After you've read the question, be sure you understand it. In this case, we're looking at the transition from some n initial value to n equals 5 in a hydrogen atom, and the line it creates in the p-fund series. Since the question states that energy is emitted, n initial must be greater than 5. The question asks you to use the Rydberg-Bohr equation to calculate the wavelength and energy that correspond to the longest wavelength line in the p-fund series. Longest wavelength means we're looking for the transition that emits the least amount of energy, in other words, the smallest transition. That transition would be n equals 6 to n equals 5. Next, we need to plan how we're going to approach the question. The Rydberg equation will allow us to calculate wavelength. Rearrange to solve for lambda. Remember that the Rydberg constant, RH, has a value of 1.097 times 10 to the 7, with units of inverse meters. So we'll need to multiply our answer by 10 to the 9 to get a value in nanometers. To solve for the energy of the wavelength line, first determine the energies of both the initial and the final states, using the equation En equals negative 2.18 times 10 to the negative 18 joules times 1 over n squared. Then you can subtract the energy of the initial state from the energy of the final state to get the difference. This gives us an answer in joules for one molecule. We want the final answer to be in kilojoules per mole, so we'll need to make two conversions, remembering that there are 1,000 joules in a kilojoule and 6.022 times 10 to the 23 molecules in 1 mole. To solve the problem, substitute the values for the Rydberg constant N1 and N2 into the Rydberg equation. Remember that N2 must be greater than N1. Calculate the wavelength and convert into nanometers, making sure that the units cancel properly. So the longest wavelength line in the p-fund series is 7,458 nanometers. Go on to the next slide to calculate the energy of the longest wavelength line.